First of all, I'd like to thank the organizers for giving me a chance to come and give a talk in this very nice city of World Heritage. So I came here last time more than 20 years ago when I was an undergraduate student for holidays, and at that time I never imagined that I would someday give a scientific talk in such a huge auditorium in this particular city. So I will talk about two-photon ionization of atoms in ultra-short extreme ultraviolet laser fields, and I put only my name here. Where is the laser pointer? This one. Okay. Yes, and of course I have co-authors and collaborators. So co-authors are Nikolai Kavachnik, who must be somewhere there, and Andrei Kazansky and Kyoshi Ueda. So, and here are my long list of my collaborators. This photo shows my groups. We are only 4 plus 1 undergraduate students. And this guy must be here too. And this guy, Takeshi Sato, will present a poster tomorrow on first principle, so time-dependent first principles simulation of multi-electron atoms in intense laser field. So I would like to invite you to this poster too. So, and here is a long list of my experimental collaborators who contributed the work presented in this talk too. So as the title suggests, this talk is about two-photon resonant two-photon ionization, or two-photon ionization. And of course, this is one of the oldest and best-known nonlinear optical processes. And we can consider single color as well as two-color two-photon ionizations. And the main message of this talk is in the femtosecond regime, or even attosecond regime, two-photon ionization photoelectron angular distribution varies with pulse duration for this case, and XUV-IR pulse delay for two-color case. And in the following, I will explain why and how. Yes, okay, as ultra-short intense XUV pulses or fields, I consider 2 different sources. The first one is XUV free electron lasers, like SCSS or Flash or Fermi in Italy. And the other ultra-short intense XUV source is, of course, high harmonic generation source, which enabled even attosecond pulses. And anyway, let's consider the process within the perturbative regime, so which is okay in this particular talk. And oh, what's happened? Okay, I skipped this talk and part, and so okay, as I already explained, the emergence of ultra-short intense extreme ultraviolet light sources such as FEL or high harmonic generation has raised renewed interest in two-photon ionization of atoms. And recently, indeed, many experimentalists measure especially photoelectron angular distribution measurements, and mainly using with rare gas atoms. And this process can be analyzed using the second-order time-dependent perturbation theory. And here is a textbook formula for the complex amplitude of the final state after the laser pulse, involving the sum over all the intermediate bound and continuum states. And here you can see a dipole matrix element here and here too. Now, we can go to the spectral representation from this to this. Then we have 2 terms in the final result. And so from the form of each term, we can identify that the first term involves the resonant, the contribution from the resonant part of the spectrum, and which correspond to the so-called resonant path in which the atom is rarely excited, so involves rare excitation, and this state is further ionized by a second photon. And the second term is from contribution, comes from the contribution from non-resonant part of the spectrum, and which involves all the other intermediate states, and probably it involves no real excitation. And it should be noted that, so even if the central wavelength is perfectly resonant with a certain level, like this, these non-resonant contributions via the other unexcited levels are always present. Now, of course, this is not my discovery. It has been long known. But if you use, say, longer pulses like picosecond or nanoseconds, you easily forget this part. And look at this imaginary unit, then because of this imaginary unit, we can somehow consider the phase between this and this, formed by this and this, by drawing like this diagram. And this delta F is indeed the phase of the complex amplitude CF. And this phase of the complex amplitude is, so affects the photoelectron angular distribution indeed. And photoelectron angular distribution stems from the interference of the S wave and D waves. Okay, for the case of hydrogen and helium for simplicity. So, and in this case, and this formula involves here scattering phase shifts here and here. So they are just the properties of atoms, and it has nothing to do with the parameters of optical pulses. And then let's define the amplitude ratio between the S wave and D wave, and also the relative phase between S wave and D wave. And this relative phase, delta, is composed of the scattering phase shift difference, and also the extra or additional phase shift difference, which comes from the phase of complex amplitude. And since this part, this term and this term depends on the pulse parameters in a different way, we can expect that the photoelectron angular distribution from resonant to photoionization depends on the pulse shape, like pulse duration or maybe a pulse Pomporo delay. And if there is only resonant pulse, or if only non-resonant pulse is dominant, we don't have, so this term disappears. So we should have delta which is equal to just the scattering phase shift, or pi minus that value. But we expect that if both paths are co-present, the relative phase is different from the scattering phase shift difference. And we have confirmed this expectation using the TDSC simulations for hydrogen and helium. And here we plot the phase shift difference as a function for photon energies. And the red curve is for 7 femsecond pulse, and blue curve is for 14 femsecond pulse. And for the case of helium, only I plot only 7 femseconds results. And this solid line, so black solid line here, are the scattering phase shift difference. And this dashed line, here, dashed line, are pi minus this value. Okay, and we can, as expected, we can confirm that at resonant positions like this here, or even here and here, so we confirm that the relative phase deviates from the value from scattering phase shift difference. And we can also see that at Rydberg region, the delta, the phase shift, is quite, phase shift difference, it deviates quite largely from the value from scattering phase shift difference. And we can also see that the transition between Rydberg states or bound states to continuum states, it's quite smooth or continuous. And briefly on the method, so we solve the time-dependent Schrödinger equation. And for the case of helium, we solve the 2-electron time-dependent Schrödinger equation using the time-dependent close coupling method. So I don't want to go into the details of the method. And now then we compared with the measurements for the case of helium. The measurements was done using SCSS EUV FEL. And here, the comparison between measurement and simulation at 4 different photon energies. And the first one is non-resonant, but they are somehow resonant. And here I plot the phase shift difference as a function of photon energy, so, and at these 4 photon energies. And as we expected, the phase shift or relative phase is different from this blue line. So this blue line is scattering phase difference. And these values deviate from this blue line, or the contribution from scattering phase shift. And I also want to say that this red curve are measurement and blue curve are simulations, and they agree with each other quite well. And on this plot too. So for the case of FEL, it's not easy to change the pulse duration, but it's easy in the simulation. So we have calculated the, how photoelectron angular distribution depends on the pulse duration. And actually, it dramatically depends on the pulse duration if you use a very short pulse, like shorter than 20 femtoseconds. So here you can see this is for the case of 2p resonance. And as you can see here, the angular distribution dramatically changes with pulse duration. And around, at 20 femtoseconds, it reaches more or less long pulse limit. So in order to, and here I plot the phase shift difference as a function of pulse duration. And please look at the red circles for relative phase. And at short pulse duration, it's largely different from the scattering phase shift difference, but it tends to this blue line at long pulse limit. And I hope someone of you, so some experimentalists, can measure such a wave pulse duration dependence. Okay. And in order to understand this pulse duration dependence, we come back to this textbook formula. So up to now, we considered spectral representation, but if we assume a Gaussian pulse envelope, we can explicitly derive the final formula, analytical formula for the complex amplitude, which looks like this, and which involves so-called Dawson integral, which looks like this. And far from the origin, it behaves like a Lorentzian function. So, and as from the form of each term, we can identify that this corresponds to the resonant pulse and this corresponds to non-resonant pulse. And as you can see, so since since this term and this term depends on the pulse duration, so capital T, in a different way, in a largely different way, we can so that the pulse, so this leads to the pulse with dependence. So this is the interplay between resonant and non-resonant pulse. So in summary, up to now, so resonant two-photon ionization is composed of resonant and non-resonant contributions. They interfere with each other, they interplay with each other, and even if the central wavelength is perfectly resonant with a certain level, this process is always there. So probably this is negligible for longer pulses, but if you use femsecond pulses or arcsecond pulses, both play a role. They are comparable, and the relative importance depends on the pulse width for femsecond pulses, and it may affect photoelectron angular distribution. And the same discussion also applies to two-color two-photon ionization. So specifically, let's consider XUV plus IR two-color two-photon ionization. And such experiment is done also with high-order harmonics and also with free electron lasers. And in such a case, okay, the IR is delayed with respect to XUV pulse by some delay time tau. Then the electric field can be described in this way. So if we input this into this formula, and then after some algebra, we obtain the final form like this. Again, this is resonant contribution, and this is non-resonant contribution. And as you can see, each term depends on tau. So this indicates that, again, so photoelectron angular distribution depends on the pulse delay. Then let's look at more closely. So for the overlapping case, so where there is no time delay, then this and this becomes 1, and both are important, so the relative phase is different from scattering phase shift. And then let's consider two separate pulses. So if two pulses are completely separated from each other, and usually, or of course, we expect that, okay, XUV excites one level, and then this level is ionized by a second IR photon. And this can be confirmed by this formula too. So this is the final formula. Okay, this may be not surprising. I wouldn't be surprised at all. But if we look at this and this, there is some difference like this. Okay, and actually this term comes from the second term, which originally came from non-resonant contribution. So this may indicate that actually the distinction from between non-resonant or resonant may be ambiguous in a sense. So anyway, we expect that the photoelectron angular distribution must depend on pulse delay. Then we made experiments. Then again using SCSS free electron lasers, and with a neon atom as a target atom. Okay, and due to a large timing jitter of Sashi type FEL, we couldn't continuously change the time delay. Instead, we checked only overlapping case and non-overlapping case. And we can see a good agreement between simulation, TDSE simulation within the single active electron approximation, and measurement like this, and here too. And we could confirm that actually the photoelectron angular distribution depends on the pulse delay. Okay. Then, okay, so it is, but in the simulations, it's easy to continuously change the time delay. Here's the result for argon and neon atom. And here we consider usual representation of photoelectron angular distribution using beta 2 and beta 4 parameters. And here we plot how they change with delay time. And here specifically we considered 8 femsecond FEL pulse and 30 femsecond infrared pulse. And we can clearly see the transition from overlapping case and non-overlapping case. And up to now, so we have looked at energy integrated, say, photoelectron angular distribution or relative phase or other parameters. Now, so let's briefly look at energy resolved delay dependence. So here is, okay, so the result are TDS simulations for a hydrogen atom. And here we plot a photoelectron energy spectrum as a function for several values of delay. And this color plot, 2D plot, is again photoelectron energy spectrum as a function of delay. And for a long path, for the overlapping case, this is this black curve, we can see a broad spectrum superposed with some resonance structure. And this actually indicates the co-presence of resonant and non-resonant paths. On the other hand, for long pulses, like 80 femseconds, this yellow curve, so this spectrum is composed of discrete peaks corresponding to resonant to photon ionization. And on the right-hand side, we can clearly see the transition from overlapping regime to non-overlapping regime. So one interest point is this line. This line is given by actually so Kepler orbit period, and as my previous 3 minutes, okay, the previous speaker pointed out, actually this Kepler formula is applicable for quite so lower Rydberg states. So, and here is the energy resolved delay dependence of relative phase. Okay, relative phase minus scattering phase difference. So again, here is for several, okay, the main part of the spectrum is between 1.1 and 1.4 electron volts. And okay, and here so this is between here and here. Okay, so this is phase shift as a function of delay. So we can see that at zero delay, the phase is finite, so extra phase shift is finite, but this tends to either 0 or 2 pi, so effectively 0 at a long delay limit. But it is interesting to see that the transition to 0, like this, depends on photoelectron energy. So sometimes, in most of the cases, it monotonically decreases to 0, but sometimes increases to 2 pi, and sometimes this oscillates like this green curve, and tends to 0 at long pulse limit. So this such a interesting behavior is reflected on this 2D plot. Actually, at some resonant point, between resonant point, there is some strange singular point. So in summary, so we have studied two-photon ionization theoretically and experimentally. So this is one of the oldest and best-known nonlinear processes, but new femsecond XUV sources have raised renewed interest, and one key concept is interplay between resonant and non-resonant paths. This can be controlled by pulse shape or pulse duration or pulse delay, and indeed this photoangular distribution varies with pulse width and XUV IR pulse delay. So thank you for your attention.
Yeah, thank you very much, Kenichi. We have definitely time for questions. So if there are no questions, then I ask you one.
Yes.
So can you make a relation of your phases you observed to the time delay which was observed in the attosecond experiments by Ferenc Krauss, where they have
this for the electron emission delay?
Yeah.
Okay, so it's not directly related to each other, I would say.
But it's essentially also phase shifts which come through complex phases from matrix elements,
yes,
right?
that's true.
Like Wigner time delay and so on.
Can be put it on the screen?
Could you please put it back on screen, the talk?
Okay, in the case of, actually, yes, you are right. And in a sense, how we can, okay, maybe this one. Okay, some relation with this photo emission delay experiment is actually this part. Actually, this is over the threshold to photoionization. And in this case, this is always finite difference from scattering phase shifts. It means this gives additional phase contribution or delay contribution to this photoemission delay experiment. So because such experiment always uses the second laser for either for streaking or rabbits.
Exactly.
And that.
Okay, thanks. So, please, there's a question up there. Camilo, right?
Hi, Kenichi. I want to ask you about this applicability of the your second order perturbation theory for two-color calculation. IR must be much weaker than UV pulse, or
The second pulse?
I'm asking about this your applicability of your second order perturbation
Theory.
Yes, the IR must be much weaker than UV pulse.
Just a moment. I will look for the slide. And I'm sorry that intensity is not shown on the slide, but anyway, at least in experiment we don't see the second satellite peak, so the intensity is sufficiently weak for the perturbation theory.
You mean a higher order
higher order
side
peaks?
bands,
No.
Okay. But you don't know about from your theory.
From our theory, we know. So we use the intensity which was used in experiments, and we didn't see the second side bands. So
Okay. Thank you.
I'm sorry that we didn't put the intensity parameters.
Then I think we should thank Kenichi again for his nice talk.